Good morning, everybody. Assalamu alaikum rahmatullah barakatuh. I hope this morning is a very good morning for us. And OSPO Media Training Academy is honored to cooperate with LS of South African Radio Communication Services on this workshop, DVB T2, second generation digital tourism TV broadcasting. We are welcoming Mr. Dr. Koenie Schutteal, Chief Executive, and we are glad to be with him in this workshop. Please mute your microphone, everyone, and if you have any question, you can raise your hand. Okay, Mr. Schutteal, you can begin.
Okay, thank you. Can everyone hear me?
Yes, sure.
Okay. Okay, thank you very much for the opportunity to present on basically DVB-T T2, which obviously flow from DVB-T1, and the previous technologies that we looked at during analog television. So I will start off with just a general presentation on where we are currently, and also a little bit of background on what has happened in the world. I will give a little bit of background also when I start off now, in order to just give you a little bit of history. We've been involved, or I myself have been involved in analog television for many years, where I initially worked at a signal distributor, Centec in South Africa, for 15 years. After that, I went to the regulator, which was the IBA at that time, which was only for broadcast regulation. We then started preparing, that was from 1994 till 99. And then already we started preparing for digital television, initially for DVB-T1. And then because T2 came along and it offered a number of improvements, we then started looking at T2. But I left the regulator in 1999, after which I basically joined LS Telkom. And we continued with the work at the time. We also prepared the DTT frequency plan for the implementation of T2. So we first had a plan for T1, and then we moved over for a plan for T2. If I have to think back about that time, I think the huge improvement from T2 to T1 was basically the fact that one could run much larger SFNs, single frequency networks, and we could then, although it wasn't sort of generally accepted, you could cover a full country with a single frequency in a SFN environment, which was for me the biggest advantage if one look at the whole offering of T2 at the time. Obviously, in the interim, we've got ATSC3, which came along and which is being deployed in the USA, very successful. It offers a little bit more than perhaps T2. And then now at the same time, we're also looking at 5G broadcast, which is currently not for high volumes of presenting to large screens in a fixed environment. It still is focused on very small screens and your handheld devices, but we will probably in about 5 years' time have something new there, which will bring additional advantages compared to what we currently have with DVB-T2. But in generally, DVB-T2 definitely form the basis for any sort of high volume of broadcast transmissions, digital broadcast transmissions currently. Okay, so that's more or less regarding the background. So we will now start off with the DVB technology in general. I think you're all familiar, and I'm not 100% sure on what you are running currently within the different ASBU states, but obviously there's definitely some digital transmissions which is going on. There's still probably analog transmissions. And if we look back at from 1950 to say 2020, yes, a lot of things has happened. Some countries obviously moved much faster than others. And then if you look at the DVB family, there was obviously a DVB-S for satellite services. There's also DVB-T for your terrestrial services, and then DVB-C, which was then for your cable services. If we look at around the world, obviously in some countries, especially African countries, there were very little cable just because of the cost of that at the time. In the interim, fiber came along, and that has also changed the whole environment for the deployment of DVB-T and other technologies. So yes, you can see here at the same time where we were looking with the analog technologies, we had a sort of obviously an analog signal with certain sort of low quality pictures, or relatively low quality pictures, and one was losing especially definition and quality of the picture with a reduction in your signal level. And now with the digital, it's either there or it isn't there. But again, the fact that one can actually have, depending on what your requirement is, either 5 standard definition programs in a, say, a 8 megahertz channel. You can also push it up to maybe 22 or even more, depending on what your transmit configuration finally is. And there again, it also depends on the density of your transmitters that you deploy in the full network. Okay, so some of the figures obviously has changed during the last few years, but not so drastically as it happened until 2015 and maybe even up till 2020. So we were sitting with the different standards where you've got ATSC3 mainly in the US. And that was also only launched now more recently in the last 5 years. They had their repack for ATSC3. Then if you look at countries in South America, they were mainly concentrating on ISDBT, and ISDBT was also the standard for Botswana. And then it was obviously, it was a Japanese standard, and it was introduced from Japan into a number of countries. And what we've seen in Botswana, yes, they started off with ISDBT, but it wasn't long before they also decided they will make the DVB-T standard also an acceptable standard in Botswana, just because all the neighboring countries were all on DVB-T, and it made it difficult for them to get access to receivers as receive equipment, because they were the only country around there that were actually decided on the on the ISDBT standard. Then you've got DTMB standard, which was more towards Asia, or a part of that. But you can see on the mapping and also on the population figures, obviously the DVB-T and DVB-T2 was the standard that was preferred, especially for region 1. Yeah, so that was probably at this stage still the most successful deployment for terrestrial television. But at the same time, if we also look at the satellite distribution, DVB-S and S2 were also extremely successful. So yes, we just have a number of figures here on different combinations of DVB-T, DTMB, and ISDB-T implementations. So we look at the number of countries here, and we also we look at the population. So one can clearly see here that the DVB standards as a total is definitely dictating the deployment of any digital standard around the world. And then you've got the other standards, which is really quite low down. And also depending on some countries having more than one standard, you can also see that that wasn't the way to go. Only a few went for those standards, just because of the low volumes and the little benefit you can get by having one dominant standard with high volumes of equipment, which will bring down the pricing of the receive equipment. Okay, so if we look at the number of countries that was investigated in the study, we can see where we looked at basically 196 countries. The number of countries that started in 2017, digital terrestrial television was 111. And at that time, only 85 was not, didn't make any move. What we've seen in a number of countries is that if you're planning for the digital standard is not up to date and also supported by the country as a whole, the success for implementation is not good. Because you've got all these competing standards nowadays, which is coming in some cases from satellite, and now also on actual internet-based sort of delivery, that many countries that were so-called successful in reaching the target of deployment of 2015, if one look at it holistically, you will see that they weren't really successful. They have 1 or 2 programs on air. And then if you look at the capacity in an 8 megahertz channel, where you can perhaps have 21, you can't really call it a success. The success is more linked to just the fact that they managed to deploy a network from a technical perspective, but the programming was not always there. In some cases, the receivers was not there. And even if you look at South Africa, the first sort of transmissions started, which was implemented by the signal distribution Centec, and they already had programs on air in around about 2010. But even up till today, we are now only close to switch off the last analog television transmitters. So the opportunity for a successful deployment was interfered by not the availability of receivers, receivers not being subsidized, just competition from other sources like satellite, which was pushed by private broadcasters, so that we will, at the moment, the appetite for DTT is not really there as it should have been. And it was all just due to no fixed policy on how we're going to deploy it, and making sure that the variety is there on air, which was in many cases on air by the satellite broadcasters, which offered a bouquet of 50 or in some cases 100 or 150 programs, terrestrial aside. And now we battle to have that appetite again for people putting up fixed reception antennas, terrestrial fixed reception antennas for terrestrial. So apart from the population coverage, one should also look at the analog switch off. So at first, yes, we looked at the number of countries that managed to get involved into DTT. If we look at the number of countries that were successful in reaching the target date of 2015, there were only 72 that were actually successful in reaching that date. So, and that reflects 37%, and 63% were not successful. Okay, then one can also look at the statistics from the networks that were deployed. So if one look at the network coverage for 51 countries, you will see that the maximum and minimum coverage area was like between 25% of the population and 100%, and with a median figure of about 95% of population coverage. So obviously, if one look at a graph of the coverage, and you want to cover 100%, you find that it's becoming exponential number of transmitters that's required to cover 90% or more. So what we've seen in a number of countries is that they were definitely cherry picking, and they only went for maybe all the main cities, covering the main cities maybe with 10 transmitters out of 180, and then reaching maybe close to 50% of the population. So that was quite common. Then you can also look at the number of muxes that's deployed. So if you look at this, say 59 muxes deployed, and then if you look at the number, yes, the minimum and maximum, many of the broadcasters would only go for maybe 1 mux or so, and you can see here on average there were 4 muxes. If you look at the frequency plan in the UHF, and we look at channel 21 until channel 48, and we've got 28 muxes, it will very much depend on your frequency plan, on what you can deploy. But if you had to cover the full country with one frequency, and you use all your channels, then you can have 28 multiplexers there that you can use in a country, and if you can then times that maybe by about 21 programs per multiplex, which will give you a very large number of programs that can be available. But that will very much depend on the actual frequency plan that you develop for your country. In South Africa, we've got quite an effective frequency plan, but in that case, we only have 7 muxes or 7 frequencies per area. So the South African plan was done on a provincial basis, so we've got 9 provinces, each offering 7 muxes. And currently, we only have 2 muxes for the free-to-air and for subscription services, which is currently on air. and that's not on a national basis. It's only for the private broadcasters. They went for about 100 sites per MUX, and the public broadcaster went for 182 transmission stations per MUX to get better population coverage. But since then, they also started switching off due to the high cost of running some transmitter stations, which has got a lot of OPEX that's required to run those stations. So you can also see here that the number of free-to-air channels in this study, we looked at 62, 62 countries, and then an average of 3 to 70 with a median of about 12 on average. Then you can also see, so there's national free-to-air, and then there's also regional free-to-air. And then there where we are sitting with, in this study again, the number of regional free-to-air was 23, and there was a minimum of 1 and then a maximum of 298. Yeah, channels per region. But also again with a median of 14. And then if you look at the commercial, yes, they were less than the free-to-air, but again, 41 countries that were investigated, and they were between 0 and 60 with a median of about 37. So you can see that the commercial broadcasters really have got a much higher median because they realize that they need to offer as much programming as possible to get the viewers to view their programs. And all these are important also for you when deploying a DTT network. So again, if we look at these sort of figures for a study that was done in the EU, and you look at DTT versus terrestrial cable, satellite, and broadband. Yes, there's the terrestrial is 43%, cable is 29%, satellite 24%, and then broadband 12%. What is important here, and that is that, yes, broadband, and if one look at broadband, you are mostly looking at broadband and 5G broadcast, or 5G that can be deployed, but it will take time from the recent studies that's been done to get this figure very high, especially to be competitive with the terrestrial stations. The focus, maybe just as background also, of 5G broadcast. If you look at 5G itself, it was created, or a lot of money that was pushed into it is for vehicle automation. And so the entertainment systems in the vehicles are going to look much different in future than it looks currently. And then for the terrestrial or the broadband network to carry a bouquet of services to each specific individual, put a lot of demand on the bandwidth availability, which is currently not available. And so we will probably still have this tendency of these graphs for quite a while, because the broadband is just not at the moment capable of handling individual requirements of each viewer out there to have enough bandwidth to actually comply to the requirement out there. Okay, these are just some figures of the percentage of people watching DTT in the EU. And you can see there's huge differences between 90% and in some cases 7%. But this again, if one look at this, you will see that like in the UK, there was a lot of effort and lots of money put into DTT and the way it was launched, and there were millions spent, millions of pounds spent on just the actual marketing of the system, and eventually they reached about 55%. And then you can see in Germany, yes, it's actually low. In Belgium, it's low, and yeah, many other countries, there's also a very low percentage of people that's actually watching that. Okay, so apart from the DVB standard, you also have MPEG-2, MPEG-4, and HEVC, which is source coding. And if one look at the contribution of the efficiency of data transfer from point A to point B, you can actually see that these sort of source coding, which basically ensure that the data is well packed as a medium, offer actually a huge advantage. If we didn't have this, the digital terrestrial television would have suffered, and it would probably not have been a medium which was effective for transmissions. So you can just see also with the different standards of HEVC and then MPEG-4 and then MPEG-2. So using a standard television channel with MPEG-2 so it just gives you a standard television, and then if you go to ultra high definition, with HEV, it's as effective for an ultra high definition channel as it was in the past for a standard definition channel. So it's extremely important that from the studio side where the stream is actually coming, that is the best sort of coding system or source coding system that's being used in order to pack in as much channels, because your viewers also currently, they are definitely spoiled by other media that provide programs of very high quality, and especially if one is looking at sport events, etc., where you need a very high quality and a high definition picture, that one need to consider from the start that your source of the programs are well coded, and then thereafter you will look at your actual transmission and decide on what the capacity of each of these PLPs is going to be, but we will get to that a little bit later. So maybe just to look at it a little backwards, obviously you need to ensure that your frequency plans are in place. You need to have a plan for your signal distribution part. You need to have a plan for your viewers part. You need to have a look at your subsidies of the receive equipment. And then you also need to look at it from a studio perspective to make sure that you will end up with a successful implementation. Okay, so apart from that, so you also need to look, especially if you look at HDTV, high definition television, the content need to be there. So, and especially the language is important, or if you are going for translations of programs, one need to look at that from a start as well to make sure that there is enough content available for the country in line with the actual regulations, which is issued by the regulator in the country. Then obviously you need to look at your consumers, and your consumers is definitely expecting a high quality TV picture. So where it in the past was analog, which was poor quality, then we went to standard definition, we went to high definition and ultra high definition. You need to look at all of that. Obviously, each time going into a higher resolution, you will need more bandwidth to actually transmit that specific program in the multiplex. Then you also, the quality of the flat screen televisions is much better. So people also then expect to get on that television that they are buying the ultimate sort of quality programming that can go with it. Then you obviously are competing all the time with the other media, which can be cell phones or other portable devices. And there one need to look at how things has changed from the older people to the younger people and what they prefer to view. So you need to ensure that you also have got content for the younger generations, that your DTT network that you deploy is not eventually just a success on paper, but with very little or very few viewers out there. Then the efficiency of the spectrum use, that is definitely the regulator's responsibility, because you can have a certain number of channels available in your UHF band that you can use, but there again, you need to make sure that you do the necessary planning to ensure that the final constellation is of the highest quality. And there you will also see later that you can have a channel that can, considering your Shannon limit, you can carry up to about 50 megabits per second. But that is with a very dense network with many transmitters. But then you can, with a sort of an average network, you will probably sit around with around about maybe 22 megabits per second. And there it will depend then on the number of HD channels and standard definition channels that you want to transmit on the number that's finally being transmitted. But at that same time, you also need to look at multiple frequency networks and single frequency networks. And obviously, the single frequency networks is the most, and there you need to take advantage of that and design your network with the minimum interference in the network. And so there again, T2 offered much better SFN efficiency than the T1 network, because your guard interval is too short in T1 compared to T2, and T2 allow you for larger SFN networks without any interference within such a network. Okay, so if one look at the key requirements for DVB-T2, so you want to get benefit from the existing installations on the transmitter side, obviously also on the receive antenna side, to keep the changes to the receive network to a minimum, also on the transmitter side. We are all aware of the recent developments that the WRC, the last few WRC World Radio Conferences, which has allocated a lot of spectrum to IMT, International Mobile Telecommunication. And there, yes, depending on where you are, you will probably sit with primary television channels only up to channel 48. And in some cases, it might go a little bit further. But from 48 to 68 was anyway, 20 channels was reduced, and that has left much less capacity for broadcast transmissions. But at the same time, one can also look at what DVB-T and T2 brought along. And so it's not that we necessarily have too little, although giving away 20 channels, 20 UHF channels, in most countries, and not all those 28 channels that's still available is all being used. I think in most countries, you'll probably find that maybe only 50% is being used, especially if, or less, if it's a SFN network. So if we just look at DVB T1 and T2, so there was typically an improvement in capacity of 30% in T2 versus T1. Then there's also the improved single frequency network performance. So if you just look at the capacity, that's one thing, but if you take capacity together with single frequency advantages, and especially large SFMs that can be deployed in T2, the benefit is, it should be much more than 30%. Just because of the fact that you can use one frequency to cover a complete country. And that frequency can then is used as a multiplex with, say, 21 channels in that frequency. Then something else, yes, with T2, there's also better robustness, there's more forward error correction, there's sensitivity improvements because of the QAM that's being used. So yes, T2 definitely offers something much better. Then the flexibility on the bandwidth and the frequency, so we can support 6 megahertz, 7 megahertz, 8 megahertz, and so it might the standard itself is very versatile in accommodating your specific current frequency plan that's available within your country and in your region. Okay, then also with the masks that's been developed, you can then deploy the same or different technologies together with analog, meeting that spectrum mask requirement in order to ensure that you don't interfere with other services, either in your country or in the neighboring country. So also, if one look at if we go back and we look at analog television, typically with analog television, we were looking at co-channel protections of around about 40 dB, where now with T2 versus T2, we are looking at around about 20 dB. And then on adjacent channels, you can deploy them at the same site. So there's also a huge advantage. Okay, so if we look at the T2 versus T1, so there's many new transmission options. You can go up to 256 QAM. That will give you obviously better sensitivity, but you can play around with the network and you can eventually either go for robustness or you can go for capacity. You need to eventually decide what's the most critical, and by making it less robust, then obviously you can fit in more channels. But if you want then robustness, reliable signal. Okay, we can also need to look at the guard intervals and the FFT modes. And the guard intervals is obviously very important in the SFN designs of your network. There's 8 different pilot patterns that can be used. There's the extended carrier mode. So if you want to push it and you want to use all or more carriers, you can increase capacity, and it's easy to arrange that in your transmit configuration. Then there's also rotated constellations that can be implemented. Then there's also MISO configurations, multiple input signal output, and there again, so on your antenna side, you can make some changes there to improve the signal quality that's being transmitted. There's peak to average power reductions, which can save a little bit on power, etc. And then you've got your multiple PLPs, physical layer pipes, which is also bringing a lot of flexibility to the whole transmission network, because that gives you the capability of having a very robust signal and a high capacity signal in the next physical layer pipe. So you can decide how large those individual physical layer pipes is going to be, and that will determine the coverage. So you can have different coverage sizes in one transmission. Then, yes, with DVB-S2, the forward error correction, which is BCH and LDPC algorithms that's being used to improve the forward error correction. And then also time interleaving. And then there's also future and extension frames that can also be used. So this slide here basically just demonstrate that you can have in one transmitter tower, you can have high definition, standard definition, and then in the third maybe a mobile signal. And you can configure these all differently to make sure that from one transmission in that multiplex, you can some programs being focusing on fixed reception, others on mobile, and others on portable or sport or whatever, in accordance with your actual program that you want to transmit and the audience that you want to reach. So that gives you a lot of flexibility in making sure that you look at all those different viewers out there. Okay, so this is more of a coverage diagram, and it also give you background on the versatility of T2, and also giving you a comparison of T2 and T1, and also different configurations of T2 with different modulations, but eventually looking at different minimum usable field states. So if you, for example, look at this, and we are looking at the E-min value, which is the minimum receive level value, then you can, with T2, you can, with a certain configuration, you can end up with 84.6 dB microvolt per meter. That's be required for T2, which will give you a capacity of 25 megabits per second. So if you had, say, standard definition channels in there, each using 1 megabit per second, then you can put in 25 there for a T2 transmission. But if you jump then to T1, you can only have 13 programs. So that gives you a very good comparison between T2 and T1, looking at specific configurations. So you can also look there and you can see, yes, this is 64 QAM being used, and T1 it's 16 QAM. It's the number of the FFT size, which is 16K versus 8K. And then you also look at the guard interval. So you are looking at 1/8 over 1/4. So you'll find that you can run a much larger SFN with T2 than with the 1/4 in T1. We've got the same forward error, the code rate or forward error correction. Here you've got the extended carrier mode, so you've got more carriers. Here you've just have a normal carrier mode. And then, yes, you've got 25 versus 13.3 megabits per second. The middle column basically just show you that what the difference can be using different modulation and constellation schemes between T2, one transmitter and another transmitter. So if we then want to look at, say, for the same sort of capacity with T2, yes, you can use 16 QAM. You have the same data rate, or more or less the same. It's 13.3 versus 15. And but your minimum usable field strength is dropping to 78.4, which actually show you that you can have a much larger coverage area because there's a 10 dB difference in the receive level that you will be using, or that your receiver will require. So yes, you will have a much larger coverage area between this and this, but you will have less programs because you only have 15 megabits per second versus 25 megabits per second. So you can, if it's a 1 megahertz channel that you will be using for standard definition, you can have 15 versus 25. Okay, so yes, for this first introduction, I think that was the first part of the presentation. If there's any questions, you can ask your questions now, and yes, I'll try to answer it to the best of my ability.
Thank you, Mr. Koenie. And everyone, anyone had any question? Please, can you raise your hand or just ask? السلام عليكم ورحمة الله وبركاته مرة أخرى. أهلا ومرحبا بكم في الدورة التدريبية DTT. أتمنى أنه الجميع يكونوا الصوت واضح بالنسبة لهم. بس تلميح في نهاية المحاضرة، أتمنى من الجميع إرسال أسمائهم وإيميلاتهم ومنظماتهم إلى الاتحاد، إلى إيميل الاتحاد. الآن سوف نبدأ نواصل الدورة إن شاء الله. إن شاء الله. We'll come back to the lecture and we are please, if we send it to you, and note that everyone have to send their name and their email to the IBU email. Now we are starting the next lecture with Dr. Koenie. Welcome, Mr.
Okay, thank you for the second part of the presentation today. So we will be now looking at DVB-T1, which form the basis for the DVB-T standard and the terrestrial transmissions. So if we look at the whole standard as it is, it uses coded orthogonal frequency division multiplexing. So if we look at the coded part is the forward error correction that's being used in the technology, and the forward error correction actually allows for signals to be retrieved, or parts of signals to be retrieved that get lost during a transmission, and it forms a very important part of the whole T2 or T1 and T2 transmission stream, and make sure that it's reliable, that you don't get pictures that freezes up completely, but it constantly is updating the data with duplication of data being transmitted during the transmission. Then the orthogonal ensure that there is no crosstalk between the carriers, because you will see that where in typical analog transmissions, we basically had 3 carriers, which was the sound carrier, the video carrier, and then your color carrier. And now we suddenly get confronted with many carriers, which is located next to one another during the transmission, which will all be transmitted within the guard band or the whole actual transmission band of either 6, 7, or 8 megahertz. And this makes it quite unique compared to others. What I can also just mention about this, if you look at many other technologies, and then you will find that this is not unique to broadcast. It's used in many other technologies, also your telecommunication technologies, where they use more or less the same aspects. And then you use the third one is FDM, so it's frequency division multiplex. So the frequencies is divided up to form a multiplex to carry lots of data. So if we had to look at a typical analog television, you will have your band, and you have a vision carrier, and then depending on the actual technology that you use, you will have then a sound carrier, which is several megahertz up, and then you get to your next channel. So you've got a sort of a band there, which typically will have a filter, and you need to stay within this mask in order not to cause interference to other channels. But if you just look at, you've got a vision carrier, you've got a sound carrier, and then you've got a color subcarrier, which is, depending on PAL-I, it's 4.43 above the vision carrier. Then you will see that it's a very inefficient transmission, because you will be transmitting one program with one transmitter to many people, and using maybe 8 megahertz or so. If we then at the same time look at yeah, so you can also look at the video channel and the audio channel, and the chroma is normally different modulation schemes, where now in digital, on the right-hand side, you can see there that there's many channels. So there's N carriers, and there's a number of aspects that will also determine what the number of carriers is and the carrier spacing, and then you can also extend the number of carriers by making it more efficient, having more carriers carrying more programs, and having more megabits per second. So if you look then at the diagram here below, you can see you've got a video encoder, audio encoder, you've got a program multiplexer, and then you've got a transport multiplexer, and eventually that is then going into your final stages. It goes in a feeder cable to the transmitter, and now you've got many of these video channels being transmitted in this multiplexed configuration, which obviously make it much more efficient. You've got better quality, you've got much more capacity, and eventually, if you look at the power use of your transmitter per program, you also will have the benefit of having much less power that's required, which in effect will actually save money. Hello?
Yes, continue.
Okay, thank you. Okay, so it makes the whole transmission much more efficient. If you look at your capex cost, yes, you might pay a little bit more for the actual digital transmitter, but the OPEX cost per channel, per program channel is much less. And if you do your business plan, you will see that in a setup like this, your capex cost is eventually minute compared to the OPEX cost. And if you compare this then to analog transmission, you even score more, because you've got all these effectively very efficient transmission channels carrying up to, say, 21, or with T1, you will probably be carrying, say, 30% less than in T2. But there's, if you evaluate it from a rand or a money perspective, there's nothing that compare with a digital transmission compared to analog. It's just extremely efficient. With the cost of electricity and shortage of electricity, there's also many benefits, because you don't require what you typically require per program for analog. Okay, so this is just an indication of, yes, you will obviously not always have a completely flat transmission that's being received because of reflections and due to the specific frequency that's being used. So you've got multiple carriers, you've got plus the error coding, that's all being transmitted together with the full transmission signal. Okay, so you will also typically have a certain bandwidth that you use for transmitting all these signals, and you've got a time and a frequency and a band domain. So these symbols that is per carrier will eventually be converted, and you will have symbols per frequency, and you have a time domain where your symbol is actually being transmitted in. So as you can see, it's a parallel procedure which is then converted to a sort of a serial procedure of number of frequencies carrying the program information.
No.
Okay. So the symbols are carrying parallel with long symbol duration, and then it allows for a long guard interval duration. So we will look a little bit later on the actual guard interval and the benefit that the guard interval will bring along. Because the guard interval will determine eventually what's the size of your actual single frequency network that you can run to ensure that you don't cause interference areas within your coverage. So the total bandwidth that we are looking at is obviously the sum of the number of carriers and then also the spacing between the carriers. And that will eventually get to your, say, 7 or 8 megahertz channel. And then if one look at robustness against a simple interference by adding a guard interval, there's a huge benefit from that guard interval that's added to allow for synchronization of not only reflections, but also multiple transmitters being received within that guard interval, which can increase the minimum the receive level, which will actually contribute to a larger signal and better coverage area. And that is typically, statistically, you can get 5 dB more signal strength in such an SFN network. Okay, so here again, you can just, we just demonstrate here 8 megahertz channel. You've got the channel width is 1160 hertz. You've got 6,860 carriers, and that eventually gives you 7.61 megahertz, which is your useful bandwidth that you will be using. And then obviously between the channels you will have also a spacing. It's in order to ensure that you don't have any interference between the two channels that you are transmitting. Obviously, if it's co-channel, then there's a certain protection ratio and that need to be overcome. What one also need to look at these signals, so there's two aspects that will cause interference or that will give you coverage. So if the signal level is below the minimum usable field strength, obviously the receiver will not be triggered and you can't get coverage in that area. There's also a protection ratio. So if you've got a wanted versus an unwanted signal, then you need a certain signal to noise ratio or protection ratio. If you can, if the minimum or the incoming signal is above the usable field strength, but your transmission signal is more than the protection ratio, you will overcome that interference potential from the unwanted signal if you can exceed the protection ratio of, say, 20 dB for a co-channel. So although two signals you might be able to receive them at the same point, you can overcome the possibility of interference by overcoming the protection ratio, which is typically in the region. It depends very much on your configuration of your transmission, but say for 20 dB, yes, you need to be 20 dB above the interference signal, and then you can still have reception. Where in analog, if you typically had to have 42 or more dB of wanted to unwanted signals in order to reach coverage in a specific area. So If one then think about 10 dB, which is 10 times, and you look at 20 dB, which is 100 times, it's a huge benefit that's brought along by the full digital transmission. Okay, so if we look at the signals itself, you've got a frequency domain with a QAM that's used for modulation, and then you go in the time domain. You've got the number you've got a number of frequency carriers. You've got in the time domain. You've got your actual symbols. So if one look at it at the bottom here, you will see that, yes, there's your frequency domain with the different carriers that's being transmitted. And then in the time domain, you've got your symbols that's being transmitted in the time or in the phase part of the actual transmission. So you can also see here, you've got a certain number of distinct carriers here, and each carrier has got a unique position, especially if you do the orthogonal, where you actually change the direction. Each of these points has got a unique angle and an amplitude that is being transmitted. And then it's converted into a signal. On the transmission side, it gets transmitted, and on the receive side, you again retrieve those amplitudes and in a certain phase, and you reconstruct then the QAM signal that was created. So you also then go from time to frequency domain and frequency to time domain again in decoding of the carriers. So in a typical sort of transmission environment, especially in analog, you will always have reflections, and so you've got your direct path of the signal, and you've got your reflections. And in a typical environment, it will be a multipath environment where you've got the direct signal and the indirect path. And with analog television, you will see this signal coming in and actually form an image which is shifted in the picture, just because of the two signals being received. In a digital environment, the same happen, but you will have a guard interval which will allow you to correct for these indirect signals that actually arrive at your receiver. And that, if it's within the guard interval, it will add to your main direct path signal, and you will actually have better reception than in that environment. So it can obviously become even more complex, where you don't only have a signal being reflected from the transmitter and the mountain, it might also be, there might be buildings, and then eventually you've got indirect path 1 and you've got indirect path 2. So there you can also see OFDM systems use indirect path signals to increase the signal level. And this is a huge benefit in this environment. So again, this is now in an area where the signal gets reflected and you've got an indirect path. Obviously, if you use this receiver and you've got another transmitter at a certain point, and it also comes in within the guard interval, that will also be added, and you will now have no interference where two signals on the same frequency is being received at that specific point. Obviously, if it is that this second transmitter, but we will look at it later as well, is transmitted and it comes in outside the guard interval, it will cause interference and you will not have, you will only have field strength but not reception. You will not have coverage because it will interfere with the actual signal. If we look at the typical analog cases, there was always interference if the signal, if there's an indirect path, and it would have compromised the actual picture quality or the sound quality. Okay, so as we've said, yes, the guard interval is in between the symbol duration. So from here, you've got this guard interval, which is the light green. Then you've got the information part that's being transmitted, and then you've got a guard interval again. And the same happened all along in the time domain. So obviously with the time domain, you've got then a frequency domain as well for all the different carriers. So this only represents a time domain for one carrier. So the guard interval is the time slot between symbols. So if the signal, but we'll look at that a little later as well, is then that comes in, is going beyond this guard interval, and it arrives there, it will cause interference because at that stage, the next set of information is already being transmitted, and now you've got two signals coming in, and the receiver will not be clever enough to look at the signals being transmitted and being received after the guard interval. So here again, we can see, yes, any signal that's being received there in the guard interval is fine. You can live with that, and there will not be any interference. Okay, so here we look at the guard interval again, and we look at signals coming with a direct path, an indirect path, and indirect path 2, indirect path 3, and indirect path 3 is then outside the guard interval. You will typically have these signals that's within the guard interval adding to the signal strength, but now if this one in red, indirect path 3 is outside, it will wipe out the signal and you will have interference there. And this is now exactly what's being showed here. That signal is outside the guard interval. It's came much too late, and now it will cause interference. We obviously have got forward error correction, which can correct for such signals, but obviously depend on how much forward error correction you've got to constantly correct for that signal coming outside the guard interval. So a signal like that is considered as a destructive interferer and not as a constructive interferer. Again, in analog systems, it would always have caused interference because the analog receiver is not clever enough to look at anything coming in the front end, and it's trying to demodulate that, and then you get an interfered signal. Okay, so this again just demonstrate how the signal that's being received is treated. So there you've got your direct path, you've got your indirect path 1, you've got your indirect path 2, you've got your indirect path 3, which again, here it goes beyond this guard interval, and then if you then add up those signals, you completely transform this signal, and the receiver will not be able to correctly demodulate this, and this will cause interference, and you will sit with an interfered signal. So the only way of, in such an environment like this, to actually get away from that is to, in your planning, to make sure what your coverage area is going to be. And then you need to look and see if you have got your transmitters maybe say 60 or so kilometers apart, but your guard interval will reflect a certain distance between the two transmitters, and you then need to make sure that you exceed the area of, say, 62 kilometers, where you can cause interference between two transmitters. So then you either need transmitters to be located further apart, or you need to increase your guard interval. With T1, it's got a limit of around about 60 kilometers, and that is that's the closest that you can get your transmitters together. You can also place it closer with shorter guard intervals, but you will see that T2 offer actually a lot of additional guard interval space to allow for larger single frequency networks without causing any interference. So there you can just see that you actually need this guard interval to overcome that interference, that this signal is not interfered with. Okay, so for each transmission transmission setup that we do, you will have a certain configuration, and so a system variant, and you will have a designator. So if you look at this, so if we say this is system variant B2, it represents a certain modulation scheme, a code rate or a forward error correction. It will represent modulation, and the code rate. So, okay. But this is the one part of the transmission, the system variant, and then you've got your system, your total system with a designator as well. And so the second part is made up of the designator. So this is the number of carriers. That is the guard interval. That's the different spacing in time that it represents in milliseconds or in microseconds. And that tells you what the size or the distance between transmissions can be looking at the guard interval. So you can see, with T1 transmissions, the maximum you can get to is 67.2 kilometers. If your signal arrives from a point which is longer than 67, and you are using a guard interval of 1/4, then you will cause interference. But this was one of the biggest shortcomings of the T1 transmissions, because it limited you to having large SFN networks. Because, like we've said, the one part is catering for reflections, and the other part is catering for incoming signals from your adjacent channel, which is your adjacent transmitter being transmitting on the same frequency as the other transmitter. So if we go back and we look at multiple frequency networks in an analog transmission environment, you normally had a repeat frequency sequence in such analog networks, and it consisted of 4 frequency assignments. So it was all in groups of 4. And those 4 frequencies, so you will use 1 at one point, 2 at the second point, 3 at the third point, and 4 at another point. But then, if you look at the ones that need to be closest, you will then use 1 and 5 at the same point, and you will have this frequency repeat. So if you stay with multiple frequency networks, the MFN networks, you still don't have a very efficient setup, because you will be dependent on interference that's being caused between these code, especially the co-channel signals, which if it's not in a SFN, it will cause interference. And you can only accommodate certain number of adjacent channels. But anyway, we will get back to that. But it's just to indicate that, yes, in a single frequency network, having all transmitters having the same setup. So if I use channel, say 21 and 22 at one transmitter, and at the second transmitter point, I will have to use 21 and 22, because otherwise you will start creating unbalanced networks, and each of your SFNs will have a different configuration with adjacent channel potential interference. So you need to have a network which is the same at all transmitters, or else you will have to spend a lot of time on the planning of these of the network, because each time the interference will be different if you don't use the same frequency combination at each of the transmitter stations. Obviously, you can't go into this sort of frequency planning environment, especially with digital, without having a very good planning software, which will be able to analyze interference of co-channel, upper and lower adjacent channel, and considering guard interval in your network. Otherwise, you will not be able to just plan it in a theoretical or maybe a table manner or whatever, just looking at interference, potential interference cases. You need to do your interference analysis on an area basis, taking each of the transmitters into consideration and each of the frequencies that's being deployed. Okay, then further, which is also important, if you are trying to receive a signal, there's different modes of reception that can be implemented by the receiver manufacturer, and that will also determine how the interference is observed by the actual receiver. So if you look at the first one, so okay, they say here there are different methods to simulate the DVB-T receiver behavior in terms of the locking mechanism to certain reference transmitter, to a certain reference transmitter. So in this case, it will look at the minimum delay locking mechanism. So again, there's two aspects of this. If I have a signal there, but it doesn't exceed the minimum receiver's field strength, this signal cannot be received and it's ignored. So if we are looking from a certain point and we are looking at what the first signal is that's coming in at the receiver, it will be the first signal that exceeds the minimum receive level and which is first coming in. So it will use this for your FFT window. and anything that then comes in after that will be outside the FFT window and it will cause interference. So this is just one way in which the receiver can be set up. This depends very much on the actual set-top box manufacturer or the television manufacturer, and they will be able to give you more information on how they've implemented this. So what's also important, if there's more than one receiver being used in a network and they use different locking mechanisms, the one receiver might work better than the other in a certain area, just due to the signals that's being received there. Obviously, if you've got the same type of receivers being deployed, then you will have similar behavior between two receivers. Okay, so the minimum delay mode uses the creation of shortest time delay together with the minimum field strength for locking in order to select a reference transmitter. So it will use that reference transmitter signal as the reference receive signal. Okay, so we can again look at the minimum delay, and we can look at a certain sort of setup here, and each of these cases that you can analyze, or you will have a scenario that can be analyzed of the first signal coming in and the second signal, and there you can also see. So in this case, yes, it's looking at the minimum delay. There's a signal coming in, that's ignored. Then the first one coming in is this signal. And then there's another one. This one is also ignored. But this is the FFT window that we are looking at for interference coming in. So in this case, yes, there shouldn't be any interference because the signal is too late. If we look at the second scenario and you look at TX3 and you are looking at TX1 and then you are looking at TX2. So if any signal comes in after that window, it can cause interference and there will not be reception. Okay, so that was the first part, was for minimum delay. So if we then have a different receiver where the manufacturer has set this up, because this is normally not selectable in your receiver to set it up in a different way. It can be available, but that information needs to be obtained from the actual receiver manufacturer. So we've got a second locking mechanism, which is the maximum level locking mechanism. So in this case, it will use the signal that's got the highest field strength being received, or it's rather signal strength, because it's the field strength converted to a signal that's being received after the antenna and it reaches the front end of the actual receiver. So it's set to a maximum level locking mechanism. It looks for the highest signal that's being received, and it takes that, and that's the reference point for the FFT window, which is a certain size and or a certain length, and it will only consider then the signals in that. Then again, there can be signals that can interfere that comes in later. But if you've got the necessary protection ratio, it will not affect that signal, even if that is above the min, because you overcome the protection ratio between that point and that point. So in layman's terms, it's the transmitter featuring the highest signal level at a certain position, and it's used as the reference for time delay calculations. And that's your time delay window. So here again, it's just an example. So we will have, in a real world scenario, we will have, yes, it's the maximum level, so it receives this signal, which is the maximum level, the first maximum, well, the actually maximum level of all signals being received. It applies the TG, which is the guard interval, and for this configuration, it's 112 microseconds. The 112 stops there. So it receives the signal, it's fine. There's nothing coming in after that exceed E min or that affects the protection ratio between that signal and this signal. So you receive a clear signal and there's no problem with reception. In this case, you will see, yes, it again looks for the maximum signal, it receives it, but then there's another signal coming in. This, and it's outside the FFT window, and it's outside that guard band of 112 microseconds for that configuration, and this will typically cause then interference in the receiver. Okay, then there's also a third mechanism, and there can probably be combinations of it as well, but the third one is the main focus locking mechanism. So the main focus locking mechanism, it looks for where most of the signals is concentrated and the power that's being concentrated in that area. A group of transmitters featuring the highest field strength total is chosen as the reference. So the total of all those receivers within the guard interval, so it can start looking at this part or from the second one to here, and eventually it will say, okay, no, this is the main focus part of all signals that comes in, and it's the maximum, and it uses then that TG window will stay the same for the configuration, and it will use the main focus area as the signals, and they can then add to a higher level of receive signal. So if we look at main focus, and the main focus in this case is very simplified because we only have basically two signals here, or we've got three signals. It sees these two as being the highest, and then again this FFT window is dependent on that configuration, 8K with 1/8 guard interval, 8,000 carriers and 1/8 guard interval. That 1/8 guard interval is equal to 112 microseconds, and it sees these two signals as the main focus area, and there's nothing causing interference here that comes in later on. In this case, yes, it is again two signals being received in the main focus area. There's nothing else with which is, okay, one will have to see where the signal is actually sitting, but typically it looks as if it will be far out, and yeah, let me just see. Okay, it has got a signal here which is exceeding that minimum, and then you need to look at the level being received there compared to this and see if that is overcoming the protection ratio. If it's overcoming the protection ratio, it will not cause any interference. Okay, so I think we've gone through all these minimum or the different modes of receiver signal. What we can also do in the planning of the network, one will typically, sorry, I just want to switch this off. Okay, so again, you will need a proper planning tool where you can simulate this. So I will have a certain guard interval there, and I will have receive signals coming in this window. I can go to transmitter A and transmitter B, and I can say, okay, I want to delay a signal from transmitter A reaching transmitter B, and then I put in a delay in my planning tool. And if I then delay that signal, or say the signal at transmitter B, and then I can ensure that when transmitter A arrives there, I only transmit transmitter B signal at a later stage. Then I keep that time difference to fall outside the guard interval. And I can insert that here to put in an additional delay, and you can then build up your network with some delays where required in your network in order to ensure that there's no interference that's being caused by signals coming in outside the guard interval between transmitters. You can probably apply it to reflections as well, but it will become just much more complex. And this is typically just used to synchronize your SFN network and to put in delays from signals reaching the transmitter or the receiver outside the guard interval. Okay, so self-interference and time delay. So if we look at this, if you've got two transmitters on the same frequency, there's always the one that can act as an interferer to the other signal if that guard or that protection ratio is not overcome. So inside the orange area, the signal of transmitter B arrives outside the guard interval of the server transmitter A. So it arrives outside the guard interval of this one, because that's the cutoff point there. And inside the white area, the time of the arrival difference between the transmitter A is less than TG. So it's less than the guard interval, and it will not cause any interference there. So what we are basically saying, this is a potential interference for transmitter B. There, nothing will happen. This was put in a very simple manner. Again, if you look inside green area, the signal of transmitter A arrives outside the guard interval of the server B. So one will have to see what that level is compared to this, and if the guard interval is overcome. If it's not, if the protection ratio is overcome. If the protection ratio is not overcome, it will cause interference into this area, or it might cause an interference area in between. So the problem that is simulated here is city B is due to self-interference not covered for 100%, because there's an area of the coverage area where interference occurs within the coverage area, which is put there as a polygon. And so there's a potential interference area. Okay, so we can, if you now look at the solution, you can say change the time of arrival between the two signals so that it at every point which is not covered yet inside city B is less than TG. So this can be done by adding extra time delay, and you will typically first do this in your planning tool. You will simulate it, you'll put in the 50 microsecond delay there, and then you will do your coverage study again. So strongest interference scenario, SFN coverage, and that's the covered area and the not covered area, and you now overcome the problem. You will typically, in your planning tool, adjudicate a certain color to interference, and we can see in this case, blue is defined as covered, not covered, and you can have another color as interference if necessary. Okay, so if we now look at what we've just learned, or what I tried to convey to you. So if we say assumptions, we've got a SFN, a fixed reception, 8K and minimum delay. And then we say which designator can ensure a self-interference-free coverage. So if we had to look at the designator that can self-interference-free coverage, we need to go back to the setup earlier. And so we can say here that if we had to look at the designator, then the designator gives the interference area as a distance, and it will tell you that this distance designator can actually ensure that you don't have interference at a certain point, if you can change that, or by changing the delay. Okay, so which designator can ensure a self-interference-free coverage? That's the first question. The second one is check the receiving test point if there is self-interference and where it may occur by using designator F. So we now need to go back again, and we need to look at what designator F is, and then we can see what will change it. So I must say this is now done as an example, but it works much better with a planning tool. So if we look at F, the limitation there is this 16.8 kilometers. So if it's within shorter than 16.8 kilometers, say it's 15, then it will not cause any interference. So we need to ensure that the interference distance is happening smaller than 16.8 kilometers away. Okay. So there, if you look at, there's a distance, 15 kilometers. So this distance, SFN test point 2, that will still be within the coverage area, and that will not cause any interference. And if there are self-interference, how can you avoid the receiving test point by keeping the data rate constant? So obviously, you either need to put in a delay, or you need to have a different configuration. And so in the case, if you don't want any interference in that first case, you need to go for the maximum, and you need to look at those distances that they are apart. So the longest distance between two is 60 kilometers. So we want a guard interval that's larger than 60 kilometers to overcome all interference. So we can look there and we can say, yes, go for a guard interval designator H with a guard interval of 224 microseconds. That will give you 67.5 kilometers distance, and that will not cause any interference. And you will have an interference-free scenario there. And then potential self-interference, RX test point 2. Yes, we've looked at that. We need to go beyond 16.2, so we go for 15 kilometers, a guard interval of 15 kilometers. And then this is just representing each of the other cases that we've seen there. Okay, so yes, another hour has passed. I don't know if we want to first stop and before we continue with the third session. Hello? Hello, are you still there?
Yes, yes, I'm with you.
Okay, thank you.
Okay.
You want me to continue?
Yes.
Okay. Okay, sure. I'll continue then.
Yes. Okay.
Okay, so why T2? One is obviously looking at your sort of regional requirements. So there's historical infrastructure that need to be used, and you want to keep that the same. So you want to still use the same transmit towers, etc. You might not have cable in the country. Many countries were like that. The cities are far apart. It's difficult to deploy cable. And so obviously, yes, you need DVB-T coverage, and that will then bring coverage to all the people because there's no other competing infrastructure. The same, there's no satellite receptions due to either not being available or due to political reasons. So the only other way, if you don't have cable and you don't have satellite, you'll probably go for a terrestrial network. And then in some cases, yes, no satellite reception due to geographical reasons, like Scandinavia, or in some cases, there's big mountains that screen off a certain part of the city. So you will need terrestrial reception. Then there might also be regional and local transmissions that's required. In some cases, you also want portable TV reception, or you want mobile TV reception, and that need to then be T2 that or T1 that offers that. Okay, so the T1 transmissions was actually defined in the ETSI configuration. So this is just a block diagram of the typical components of a DVB-T transmitter. And so you've got your coder, which is the outer coder, and the inner coder, which basically allows you for the forward error correction flexibility. You've got your pilot insertion for your pilot signals, your frame adaptation. You've got your OFDM modulation part. You've got your guard interval insertion, and then you've got your digital analog conversion, and then eventually your transmit the RF signal. Okay, if we look at the mapping, then obviously you've got QPSK, you've got 4QAM like this, where there's basically 4 defined vectors in your transmit part. So this will represent a very robust sort of signal with low signal level requirements and very large area. This is sort of in between with a 16 QAM, and then with a 64 QAM, you will require more signal, you've got more capacity, it's not as robust, but you can obviously, by changing the the FEC, the forward error correction, you can make this more robust, but obviously then you will require more carriers to carry the forward error correction signals. Okay, so again, this is just, again, the different combinations of a 4-QAM that you've got there. Then if we look at the different pilots, the pilot insertions, so transmission parameter signaling is the transmission mode that's being defined. Then you've got your guard interval, which is again a component, and we've seen it before as well, that you can have 3/4, or you can have 1/4, etc., which reflects a certain distance between transmitters. Then you've got your constellation, 64-QAM, etc. Then you've got your code rate or the forward error correction, which can be 3/4 or 2/3, whatever, and that defines how many bits you are actually retransmitting. And then you've got your frame number. So yes, modulation, OFDM, guard interval, your digital to analog converter, and your RF is being, which leaves the transmitter. So this is just more on the configurations of the T1 signal. So if you've got the number of carriers that you can define, you can have 2,000 carriers, you can have 8,000 carriers, and that's the actual number of carriers which is associated with the 2K mode and the 8K mode. You've got the payload, you've got your continuous pilots, you've got your scattered pilots, you've got your TPS carriers, which is which is all indicating how many carriers there are. Then obviously you've got your carrier spacing, like we've said earlier. Yes, the carrier spacing and everything, and the associated modes will depend on the channel bandwidth, which is in this case we used 8 megahertz channels. Can also be 7 megahertz, can be 6 megahertz. Okay, and then if we look at the transmission modes, the carrier mode comparison. So if you've got the SFN size, you've got a small, so there's short symbols and there's short guard intervals. For mobility, it's good. So if you've got 8K mode, that is not good for mobility. It's bad for mobility. The SFN size small. If you want a large one, then obviously you need to go for 8K mode. So you need to balance these up and see eventually which gives you the best setup in order to, if you want large SFN sizes, yes, you definitely need to go for 8K mode. If you want mobility, yes, you're not going to have large SFNs, but you are going to use a 2K mode and you are going to have a dense network with many transmitters, because otherwise you will have large interference areas. Okay, then DVB-T, the data rate and the networks. Okay. We can again look here at the data rate for 8 megahertz channel. You can look at 16-QAM, the code rate at 1/2 and the guard interval at 1/4. So that is your effective bandwidth is 7.6 megahertz. You look at a certain symbol rate. You look at guard interval of which is 2 to 4 microseconds, and then the symbol rate is eventually so many per second. Okay, so if we then look at the T1 total configurations, you will always end up with a sort of a table like this, where you've got a certain modulation, you've got a certain carrier code rate, and then you come to your Raysian, your Rally reception levels, and there it tells you what sort of carrier to noise you will require to have good reception. So what one can see from this, we don't see the absolute minimum receive levels in this, because that's a more complex calculation. But this gives you a good indication that if you are here, you've got a very robust signal, because you only require a 6 dB carrier to noise ratio. And you can see as you go up in your QAMs, like 16 QAM, 64 QAM, you start requiring much higher signal to noise ratios, which in effect increase your minimum receive level, and your actual, you will end up at a much higher receive level that's required for reception. You can also see here how the guard interval also affect your signal to noise ratio. So if you've got 1/4, yes, you've got a very low, sorry, this is, let me just correct this. If you look at your guard interval, you will require a certain data rate. And we can see here how the guard interval size will affect the megabits per second that can be achieved. So again, so if you've got, yes, a 1/4 guard interval, it will affect your data rate. Whereas if you've got a very short guard interval, you can see you can reach much higher bit rates with the guard interval. So this is just showing the relationship between the different settings of your transmissions. And although this is T1, you will find that in T2, this is also applicable. Okay, so yes, this is then the finish of T1 presentation. And but we've done T1 first because you will see that although T2 is quite a bit different, and there's different ways of forward error correction, etc., but the basic principles is still apply to T2 as well.
Hi, sir.
Yes, I can hear you.
I have a question about the guard interval.
Yes.
Why it is related to the distance?
Because the signal, the receiver needs some, because it's a timing reception. So information gets received in a certain time, and then it needs to take that information, synchronize it, and pass it on to the next stage for demodulation. So the guard interval just gives you that time, that you've got extra time to quickly correct those signals, that they all add together and they are synchronized for the reflections that's coming in. If you don't have that time interval, then all those signals, you've got then a very instantaneous reception, and all those signals will be basically out of the guard interval. Or the chance is that many of the signals will be outside the guard interval and they will cause interference if they are, because you could see that we can go up to maybe 67 kilometers away, where the two transmitters is located from one another. So at the one transmitter, if it reaches that point at the right level and outside the guide interval, it will cause interference. But if we make it much smaller and we can see we can carry higher bit rates, you make your signal very prone to interference because you can't do that synchronization.
So in order to avoid
Is that clear?
it's in order to avoid another transmitter that are in the same distance or low distance or stuff like that.
Yes, that's correct. But that's very much applicable to single frequency networks where you use the same frequency. Obviously, if you use a MFN, a multiple frequency network, you will not be confronted so much with the guide interval because your frequency spacing will be far away and you will have very few signals coming in at such a point that can cause interference. But in order to improve frequency efficiency, you need to go to a single frequency network, but then you need the guide interval.
Okay, thank you. I have another question, but if you can go to the slide when you about the maximum level locking in the receiver's mode. Okay.
Yeah.
Here, how does he know all the maximum in the window? The receiver, how he knows the maximum?
Look, it's all about the synchronization and the time, because you also use a reference signal. So you will check at any sort of stage for these signals. So the distance here will depend on the actual guide interval, that is wide, but it will then start scanning and it will get an information from the timing signal. And it will say, okay, yes, I can start scanning here, but I'm looking for now everything after this point. And so that's got to do with the whole timing. And that's why you've got a GPS reference or a very accurate GPS reference. In the past, many years ago, we were using different types of signals in order to determine those synchronization. So it will obviously have a time. It will know that it needs to start scanning here, and it will then lock in a certain area. The way in which they determine how they are going to do either any of these mechanisms, these level locking measurements or synchronization implementation depends very much on the actual transmitter of the receiver manufacturer.
Okay, thank you.
Is there any other questions?
Please, I have a question.
Okay.
What is the difference between this maximum level locking and the main focus? I didn't understand.
Okay, so the maximum only look at the one signal that's the highest. So it's looking at the maximum signal from the start of the scanning, where the main focus, it looks at all the signals, the total of all the signals in that guard interval. So it will basically scan and have a certain window and say, if I move this across all the carriers that's being received, where do I get the maximum of all the carriers? So if we look here, we can see there's a distinct one and it uses that one. But if we go to main focus, then you can see it's actually looking, it would have started there for that FFT window and maybe go up to there. And then it says, oh no, my average or my total is something, is X, but or say 57. But then it moves to the next and it starts scanning there and it gets there. And it says, oh, there's 2 extra signals. So it all adds up. So you are looking at those maximum reception, maximum signals and the total of them all, which can include reflections. And it will then say, okay, I'm getting the biggest benefit from these signals around this area, because that will all add up and increase my total received level of signals within the guard interval.
Thank you.
Thank you. Yeah, I think there were more questions. Maybe you can just remind me of them, because I see there were a number of comments. So what I can also see with regards to some of the other questions, so obviously the guard interval is a very important...
Excuse me, there is some question about, someone said more classification about SFP. And what is the best system of the synchronization of receiver?
Yes, it's difficult for me to comment to say which one is the best, because they don't, because that's intellectual property. The receiver manufacturers don't want to discuss too much about the detail and the algorithm they are using. So one will have to test receivers, which is a common practice when you implement DTT, to take a number of receivers and see how well that fit. Obviously, in areas where it's very mountainous, etc., the receivers are going to perform differently to an area where you've got maybe a flat earth type of area. And then also in city areas and in outside areas, where you need to see what's the real benefit. So probably in areas where there's lots of reflections, but it's quite limited in size, you can benefit a lot from that in increasing your receive level and changing a typical analog interference area into an actual benefit of having the signals adding up. But it's difficult for me to just comment and to say this is the best for that area. One need to do tests on the receiver and then see which one performs the best in your area. Like I've said also, one can also in the field look at these different receivers, and if you've got 2 receivers which are set up differently, you will get maybe a benefit from the one which is not applicable to the other one. Also your network, depending on how dense your network is. So yeah, the minimum delay is just looking for the first signal that it can receive. And if you've got a very strong signal environment, you can probably live with that minimum delay, because most of your signals you receive will be of high level, of a level which is high enough to have reception.
There is some question, more clarification about SFP.
Yes, I just want to look at that SFP where that came up. Yeah, sorry, I can't recall that SFP. I need to look for it because is there perhaps a page, or can you guide me where it was mentioned? Because
Self fault point. Get me?
yeah, just say again.
Self fault point. It's a method for making friction ratio measurement.
Sorry, I can't hear it so clearly.
It's perform protection ratio measurement in standardized manner. So you can check the signal slip, how it's, is it okay or not, or there is something bad. A method of checking for the signal itself. Maybe because I attend lately, this is why I take another point. You can it's a method for check the signal quality itself. Look like PAR.
Okay, I'll make a note about this and I'll get back to you. I'll look for it maybe after the session and I'll get back to you.
Okay, okay.
Okay. Any more questions? Yeah, I don't see SFP appearing.
It is you can depend on the designated table for check the interference area, so that we can check the signal itself. Is it good or not? Doing it on the I don't know how to explain it. If you want to check the signal itself and the quality of the signal,
Yeah.
there is something called SSV. Okay, it's make protection ratio. It's talking about the protection ratio. To measure the in the case of televisions, it's two kinds. There is SFP and PR. PR, it was very, very difficult. Historically, it was very difficult to be used as a measure of measure method. So they changed it to another method called SFP to check the quality of the signal itself.
Okay.
This way, okay, we can put it as a note and we can discuss it later.
Yes, but what I can do, I will put up some practical predictions, maybe in a tool tomorrow, and then I can show you how it changes to improve the signal quality and what all the effects will be. Yeah.
Okay, good.
Yes, but you will see also if I look at, if I give a demonstration on the network processor, you will see that all these things are very interrelated. Each of these, whether you're looking at the guard interval, it will affect the receive level, it will affect the bit rate. And any sort of change that takes place there will affect that. But obviously, if we are looking at a multiple frequency network, yes, then we're not so much exposed to these interference cases coming from a guard interval. But obviously, the MFN is not very frequency efficient, and one want to move away from that. You want to rather apply a SFN, except if you know that you've got enough frequencies available, you're not going to be dependent on too many multiplexes, then you can go for a multiple frequency network and limit the whole issue about potential interference by SFNs. Yeah. But I think we are past that stage. In many of the projects I've done, people were suspicious of SFNs because you need to have better synchronization. You can also, if something goes wrong within the SFN and one of the transmitters go out of synchronization, it can cause an area that will have interference because of a faulty transmitter. But there again, the benefits of the SFN is actually much more than the disadvantages of the SFN.
Okay, thank you, sir.
Okay, thank you. Any more questions?
And there is some question here. What system I have to use if I plan DTT system first or best server?
Okay, look, there's a number of obviously of planning tools that's available. We are just one of the companies that manufacture that, but there's ATDI, there's LS, yeah, and then there's a few others in the US as well. But if I can give you a list, I'll just put a list together and I'll share that with you. But it's normally, you will need a broadcast planning tool, which will be one module, which will be for, maybe in this case, for DVB-T. Then you should just be able to simulate all these scenarios, that you know exactly what sort of coverage you can achieve, what sort of interference you're going to achieve. And then after doing that, you will be able to put a requirement of equipment together in order to get closer to the actual cost of the full network. Maybe just another comment. If you look at SFNs, SFN nowadays is so common. If you look at the cellular 4G, LTE, 5G systems, they're all using SFNs. So if that is used so extensively, we in the broadcast environment can also use it with the best sort of results that's required. You want me to start with T2 and for the next 20 minutes or 25 minutes that we can, just start that and see how far we get.
Okay, thank you very much, Doctor, for this valuable lecture, which I think everyone have get useful information. And tomorrow, inshallah, we will follow the rest of the lecture at the same time.
Okay.
Thank you very much. Thank you very much.
Okay, thank you.
Okay, welcome.
Okay.
Anyone have any question or anything, he can send it to us and we will send it to the doctor. Thank you, all of you. And do not forget to send your names into our emails. Thank you very much. The lecture, it's recorded and will be on the website after the course is end. Thank you for all. Thank you very much.
Okay, thank you.
Welcome.
Okay, bye-bye.
Bye.